So let's go ahead and get started. So today's class is just going to be a review of the material that's going to be on the exam. Hopefully everybody knows there is an exam on Monday. If not, surprise. So what I'm going to do is I'm going to go through the equations that are going to be on the exam and kind of break down problem by problem what's going to be on it. And then afterwards, it's kind of a free study session, so work on whatever it is you think are your weak points or the things that you have to work on to study for the exam, and we'll come around and answer questions for you. So the first topic, so there are 4 topics that are going to be on the exam, and luckily or happily we have 4 questions that are going to be on the exam, so it's going to be very one topic per problem. Okay, so the first topic that we talked about was the Biot-Savart Law. And so what the Biot-Savart Law allowed us to do was to calculate what the magnetic field was from some infinitesimal line element of current. And so the Biot-Savart Law says that the infinitesimal magnetic field is going to be equal to mu naught divided by 4 pi times I dl cross r hat divided by r squared. Now this portion's not going to be explicitly on the exam, what I'm going to write now, but it's useful to compare these two, because the way that we do calculations with the Biot-Savart Law is very similar to the way that we did calculations for Coulomb's law when we had some infinitesimal amount of charge. So we'll remember on the first exam we had this equation that said dE is equal to 1 over 4 pi epsilon naught dq divided by r squared times r hat. And so our Biot-Savart Law calculations followed almost the exact same way that these calculations for the infinitesimal electric field went. The only real difference was that instead of some infinitesimal amount of charge and some unit vector r hat, we had this infinitesimal dl that parameterized the direction of the current, and that's going to be crossed with the unit vector r hat. And so when we're looking at the types of problems that we could see where we would use the Biot-Savart Law, those were problems like we had for one of the homeworks where we had this square. We wanted to find if the current goes around like this. We wanted to find what the magnetic field was at the center. And ultimately what this came down to was being able to calculate what the magnetic field is produced by a finite length of wire. Okay, so that's the first case of Biot-Savart that we had, so let's call that Biot-Savart A. The second was if we had some arc of charge. Okay, so if we had some arc of charge like this, where this is going to go around like this, then we could also calculate what the magnetic field is at this point from the arc. So the real difference between these two ultimately came down to the way that we wrote what dl was. So here dl vector is x hat dx, r hat points like this. For this one, dl goes around like this, so this is dl, where this dl is going to be equal to r d theta times theta hat. Okay. Now the other difference, one difference, like I said, is between the dl's that I have in these two cases. The other difference is the way that I evaluate the cross product. So in general, when we write the cross product, dl cross r hat is going to be equal to the magnitude of dl times the magnitude of r hat times the sine of the angle between them. I'm going to call this an angle phi to differentiate from this angle theta, because these are not the same angle, times the unit normal vector n hat. Okay, so when it came to doing this case, what we saw was that this angle phi is going to be different for every infinitesimal dl that I have here. And so what we have to do in this case is parameterize this in terms of some x. If this had some height of a, then this is some a over 2. And so r in this case, r would be the square root of x squared plus a divided by 2 squared. Sine of phi would be equal to a divided by 2 divided by r. Okay, everybody with me so far? Yeah.
I just can't really read like what's in that triangle, and I think that's what keeps mixing me up.
Yeah. Let me make this bigger. So here's, and actually we don't really need the whole, because it's symmetrical, you multiply it by 4 for each side. So if this is some distance that I'm saying is a divided by 2, this is my dl. Because the current goes this way, my dl goes this way. dl is x hat dx, because I'm saying that this is the x direction, this is the y direction. And then this is the vector r, so r hat points like this. Now, if dl points this way and r hat points this way, this is the angle that's in between them. This is phi. And so I can complete this triangle here. This length, let me move this over here. So dl is equal to x hat dx. This length right here is x. Squeaky today. This length is x. This length is the length a divided by 2. Okay, and so from this, what we can say, if this is the distance r, which by definition is the distance from the infinitesimal dl to the point where I'm finding the magnetic field, r is just the hypotenuse of this triangle, and so that says that r is equal to the square root of x squared plus a squared divided by 2 square rooted. And then the sine of the angle is just going to be a divided by 2 divided by r.
Oh, that's an x squared now. It looks like an r squared from
sorry, yeah, this is square root x squared plus a divided by 2 squared. Yeah.
I have a question.
Sure.
Doesn't the right angle, doesn't it form like part of the x, not the whole entire x?
So this has to do with the way that I'm defining where 0 is. So here I'm saying that 0 is directly below the point where I'm finding the magnetic field. Remember, there are kind of 2 different ways that we could have done this, and the reason why I'm doing it like this is because if I did it like this, and this was, here's the point, here's r hat, here's r. If I say that the origin is the left side here, then this is the distance x. This distance is a divided by 2. And so when I form this triangle, the piece that I really want here is a divided by 2 minus x. And so it's actually a little bit more complicated to do it like this. So part of what I'm doing here is I'm defining x to be relative to the point that's directly beneath the point where I'm finding the magnetic field. Does that clarify things? Okay. Other questions? Yeah.
Oh, sorry. She had her hand raised.
Okay. I'll get to both of you.
I was just wondering really quickly, where do you define x to be 0 in the square? Is it at the center or at the...
Yeah, so if I'm doing the problem with the square, so I'll have the square like this. And you have a choice, but it's something that you guys should be noticing, and this is something that even carries over from last semester when we did just mechanics, is that it's very important to define an origin, right? So even if I was doing a problem like I have a mass and I drop it, what's the force acting on this mass? You could say, so we know the force is going to point down, and the force is going to be the force of gravity, mg. But you could say F vector is equal to minus mg, y hat. Well, yeah, so it would be minus mg y hat if I say that the y direction is up. But I could say that the y direction is down, in which case it would be F vector is equal to mg y hat. So even last semester we saw it's really important to define an origin. And what I'm doing when I'm defining this particular origin is I'm saying that the origin is right in the middle of this wire. So this is x is equal to 0 here. And then that makes this the distance x. This is the distance a divided by 2 if this has this length of a. It's pretty ugly a. Length of a. And then this is r. So, like I said, you could define x to be 0 really anywhere you want. There's really 2 places that are particularly advantageous, and that's one is to put it at the corner, the other is to put it at the center of the wire. And the reason why I think it's better to do it at the center of the wire is because it simplifies what this length is here. Because if I was to do this relative to the end of the wire, then my r would be equal to the square root of a divided by 2 minus x squared plus a divided by 2 squared. This is more complicated to work with. So a judicious choice of origin will simplify the problem or ultimately the calculation that you're going to do. So does that clarify why I put it there or where it is? Okay. Yeah, you had a question too, right?
It was very related. It was just to clarify, would you get into trouble if you defined 0 to be just the corner of the triangle and allowed your 0 to move with that?
So you wouldn't want to have you could do it like that, I guess. So you have like a moving coordinate system. That makes it even more complicated. So I would say fix a coordinate system. Say really the only two choices that I would make would either be here or here. You could, like I said, you could put it wherever you want. But the natural choice is either here or here, and fix that. That coordinate system stays at that point, and then you can define your triangles relative to that definition of the coordinate system. Yeah?
So, I'm not sure if I have a question. How would we see a difference if we were to define it like where you have it like pretty much beneath where we're finding the magnetic field versus
Right, so ultimately what's the difference between the two? It'll come down to the limits of integration. So when I do the limits of integration for my choice is going to go, if this is some distance a over 2, and this is some distance a over 2, my integral here is going to go from a over 2 to minus a over 2 to a over 2. Whereas if I did this one, this would go from 0 to a. So where am I starting? And you can see why that's the case based on the coordinate system that I have. If I say 0 is at the middle, I start somewhere that's not 0, and it's in the negative direction, and so this is the minus a over 2. And I go up to a over 2, as opposed to if I define the coordinate system like this, when I'm adding up all of these pieces, I start at 0, and I go all the way up to a. But either way you choose to define this, you'll end up getting the same answer, and you have to, if the physics is true. It's just a matter of really the algebra and the calculation that you're doing, and the way that you're choosing the coordinate system.
That is the only difference.
That's the only difference. Yeah, the answer is always going to be the same. And again, regardless of where I choose this, I could do something weird and put the coordinate system here. I could say 0 is here. That complicates it even more, but ultimately, when I do the calculation, I get the same answer. Yeah. I wouldn't, and part of the reason why I choose it where I do is to simplify the calculation. Because even though you'll get the same answer, the calculation itself would be more complicated depending on your choice of coordinate system. So I'd say, as a general rule of thumb, always define the coordinate system such that the origin is at the center of the finite length of wire. Yeah?
How would this change if you had a rectangle? Would you have a varying y direction and a varying x direction?
So if I had a rectangle, so what I was doing here was I was saying that all sides are the same, but let's say that this side is a length b instead of a length of a, right? So what that would say is this becomes a b over 2. The limits of integration stay the same because I'm still adding up over this length, right? I didn't change this length, I stretched this out like this. But what that does ultimately is it changes what r is, because r, instead of being r is equal to the square root of x squared plus a over 2 quantity squared, this is the square root of x squared plus b over 2 quantity squared, because then this length is b over 2. And then that also changes what the sine of the angle is. So the sine of the angle, instead of an a over 2 here, I would have a b over 2. So that's really the difference. It doesn't change the limits of integration or the choice of coordinate system or how I'm defining x here. It changes how I'm forming r, the distance, the hypotenuse of this triangle, and also the angle. Okay.
How would the limits not change that?
The limits wouldn't change.
There anymore. So b over 2 isn't going to be half of the length from the corner to the center.
Well, I'm keeping this side A.
Oh.
If I keep this side A and I change, and instead of making this a side B, instead of having these both side A's, I'm going to keep this side A and change this one to a side B. But you're right. If what I did was I said I'm going to keep this one A, I'm going to change this one to B, then the limits of integration would go from minus b over 2 to b over 2. But it depends on what side you're changing. changing. Yeah. Yeah.
So due to symmetry, your final answer is going to be multiplied by 41.
Yeah, if it's a square.
Right.
If it's a rectangle, then what you have to do is you say, okay, well, this side and this side give me the same contribution. I can multiply that by 2. And this side give me the same contribution. I can multiply that by 2.
Situation, you have to do it twice.
Yeah. Or if you're clever and you're following kind of the arguments that we're making here in terms of what's changing if I change, if this was A and this was A, and then I change this from, keep this A and change this to B, what changes for it? Then you can actually just replace the things that change in the calculation without explicitly doing the calculation again. I would be careful doing that, but if you realize that, then you don't have to explicitly do the calculation twice. But you have to realize that this gives a different contribution than this if they have different lengths. Okay. Other questions? Yeah.
When you're doing the cross product up there on the top of the board, I'm so used to being able to drop the hat once we've taken the absolute value, but is that just to make sure we don't plug in a full R there? Is that just would that just be a 1 if we actually?
So this magnitude of R hat, yeah, that's just 1 because it's a unit vector, so the magnitude is 1. But the last piece that I didn't talk about because I was talking about the R and the sign of the angle is you have to determine what n hat is, right? And the way that we determine n hat is we point our fingers in the direction of dl, curl into R hat, and so n hat points this way. There's a question? Oh, you're just doing right hand rule. Okay. Other questions about this one before I move on? Okay. So this is the finite length of a straight wire here. The other case that we could have is the arc, and the arc is actually a little bit simpler because this radius, if this is some radius of A, is always fixed, right? That's how you parameterize a circle. It's a set of all points that are equidistant from one point. So these are all the same distance from here. And then the other thing that I can notice here is that the sign of the angle here is always going to be 1 because R hat and dl are perpendicular to each other for every point along here. So for the case of the arc of the circle, dl cross R hat is just going to be R d theta as a magnitude times R hat times sine of phi times n hat. This is 1, this is 1. And so I just get an R d theta, and then I just need to determine what the direction of this is. So fingers in the direction of dl, curl into R hat, this one points out. Okay? Yeah?
Why is R hat always 1?
It's by definition. It's a unit vector, right? So unit vectors always have magnitude of 1, and that's part of the reason why we work with unit vectors is because they have magnitude of 1. So when I write a vector equation to say, for instance, R vector is equal to, I don't know, 57 times R hat. A vector is something with magnitude and direction, right? This is the magnitude. This is a direction, but they're completely separated from each other. So the unit vector doesn't have any of the magnitude information. It only has the direction information. This has all of the magnitude information. Okay. All right. Other questions about this before I move on to Amperes Law? Okay. So Amperes Law was the law that in a way was kind of analogous to Gauss's law when we're talking about comparing how we calculate magnetic fields to electric fields. And so when I say that this is analogous, it's not exactly one-to-one, but the idea is that when we use Amperes Law, we're exploiting the symmetry of the problem that we have. So Amperes Law says the integral of B dot dl is equal to mu naught times I in. Okay. So when we would use Amperes Law is when we would have an infinitely long wire with some current. And so we remember what we did with Amperes Law was we said we draw some Amperian loop that goes around this. And the direction that this loop is going to go around has to do with the right-hand rule, okay? So my thumb is going to point in the direction of the current, and my fingers wrap around in the direction of the of the magnetic field. So in this case, if the current's going this way, magnetic field goes around like this. And this tells me then that the left-hand side of Ampere's law, integral B dot dl, is going to be equal to B times 2 pi times R, because I'm going around some circle with radius R, okay? So then, and this is actually, for all the problems that I would ask you, the left-hand side of Ampere's law is always the same. So it's always going to be this B 2 pi R. What can change is what the right-hand side of Ampere's law says. So what the right-hand side of Ampere's law says is how much current goes through the area that is enclosed by this loop that I have here. And another way that we could write this is to say that this is mu naught times the integral of j dot dA. And so we can think about a whole bunch of different scenarios that we have here. So this is the simplest case where I have just a wire that is infinitely thin, but I could also ask what happens if I have some wire that has some thickness, so that this has some radius of A, and some current is going to go to the right like this. And if I wanted to find what the magnetic field was everywhere, that would be to say I have two regions, one where R is less than A, and one where R is greater than A. We would want to draw Amperian loops in each region, and then ask ourselves how much of the current passes through the loop that I have. So in the region where R is less than A, we can see that it's some amount that's less than the total current. For the region where R is greater than A, it's the total current. So in doing this calculation, when I want to find what the current is that goes through the inner loop that I have here, what I need to do is I need to define what the current density is. So by definition, the current density is going to be the current per area. And so in this case, if I have this radius of A and this current I, the current density is going to be equal to I divided by pi A squared. And I can give this some direction. If this is the x hat direction, this is the x direction, then this is going to go like this, okay? And so from this, what we can do is we can calculate what the current that passes through this is. If we say that dA is going to be equal to 2 pi r dr, and our limits of integration in this case would go from 0 to r. So what else could I change here? Well, instead of telling you what the current is, I could tell you what the current density is. That current density could be a function of the radius. And then another thing that I could change is, rather than having this a solid wire, it could be a hollow wire. Okay, yeah?
So going off of the type of wire, does it matter if it's like a conductor versus insulator kind of deal?
No, so it's always going to be a conductor. Okay. Yeah, so when we're talking about Ampere's law, you need a conductor, because if it's an insulator, charge can't flow. And so if charge can't flow, there's no current. So these are always going to be conductors, yeah.
So is that going to be a trick question that says there's no wire with those?
Well, I mean, if it was a trick question like that, the question's actually very easy, because then you could say, if I have an insulator that has some charge in it, then the magnetic field that's produced by it is 0, yeah. Yeah.
Does it matter if the wire has like finite length or not?
Yes, yes. So this has to be a very long wire. So I'd say somewhere it's a very long wire if it's infinitely long in both directions. But if this wasn't infinitely long, or if it wasn't, or another approximation you could say is find the magnetic field very close to the wire. But we hadn't really talked about approximation, so I probably wouldn't ask that. If it wasn't infinitely long, then you have to use Biot-Savart. But then if you have some geometry like this where it's not a very thin wire, then it's actually very hard to use Biot-Savart, because then what you need to do is say, for every little patch here, I have a different R that points here. I have a different angle. It's actually very complicated to do that. This ends up being three-dimensional in a way that's complicated to do the integral if you're using Biot-Savart. So I wouldn't ask something like that. Yeah.
Is your dA by definition always 2 pi over dr, or does that change?
It doesn't have to be. It doesn't have to be. So remember, when I was doing Faraday's law, dA was typically either this, or it was dx dy or dx dr, depending on if it was circular or if it was a square. Here. you couldn't have a square loop where the magnetic field would simplify around the outside of the loop. So here it actually would, with Amperes law, it actually would always be this. For the type of questions that I would ask you guys. I wouldn't, I'm trying to think of something else that, yeah, I mean, it would be very complicated to ask something else, because in that case, the whole reason why I can do this is because the magnetic field and the dl vector are in the same direction. But if I made this so that it had a square cross section like this, then drawing an Amperian loop going around it like this doesn't have the right symmetry, because the magnetic field has different values at every point around here. So it does have to be circularly symmetric. Yeah.
And then, can you explain the difference between, like, I guess, like, the current they give you, like, usually in these problems they say you have a current, like, going left or whatever, versus, like, what is iron that you're finding, like, what is that current?
Can you say that one more time?
Like, usually in these problems they give you a current, like, it's going to the left or right, but then, like, we're trying to solve for a new current, so I'm always kind of confused.
Oh, okay, so yeah, when we're trying to find a current that's produced by a magnetic field, that's Faraday's law. These are questions where I give you some current, you're meant to find what the magnetic field is. But finding a current that's produced by a time-varying magnetic flux is Faraday's law. So it's a different type of question.
Okay.
And yeah, I don't know how, because I think what you're trying to ask is really, how do I know which equation to use in which situation? You have to look at the geometry and say what's applicable here. What's applicable here is, because I have an infinitely long wire, and what is it that I'm asked to find? So here, what you would be asked to find is to find what the magnetic field is everywhere. Whereas if you had a question where you had some closed loop and you're asked to find what the current is that goes around that loop, that's a Faraday's law question.
What if you have, like, an infinitely long wire, but it has a current that depends on time, and you want to find magnetic field? Can you still use?
Yeah, it's the same thing, only here, instead of having I, this becomes I of t.
Okay.
Yeah, that's the only difference. Yeah. Other questions? Okay, so that's Amperes law.
I think she has a question.
Oh, yeah, sorry.
I'm not sure if this, I know my question applies to the questions that we've done with I don't know how to pronounce it correctly, the first.
The Biot-Savart Law?
Yes,
Yeah.
and I'm not sure if it still applies to the Amperes law questions, but I know, like, during one of our recitations we had a lot of problems with basically a circular wire, and we had to use, like, the dl equals r d theta hat. And I know this should be easy, but every time I try to actually, like, put theta hat in terms of, like, cosine and sine,
Oh, right.
I never actually get it correct.
Yeah.
Can you go over that? 'Cause I think it applies to both of these.
This, yeah. So let me finish going through the equations, and I'll do that as an example. Okay. Any other questions about this? Okay. So the next equation that we had was the Lorentz Force Law. So what the Lorentz Force Law allowed us to do was to calculate what the force is acting on a charge due to an electric or a magnetic field. So Lorentz Force Law, so this would be 3. So this said that the force acting on the charge is going to be equal to Q V cross B plus Q times E. Okay, where B is the magnetic field, E is the electric field, V is the velocity the particle moves with. Now, in the case where you have a particle that's moving through a region with only a magnetic field, which is what a lot of these problems were asking, the electric field is 0. Okay. And so this allowed us to do a whole host of problems to say if I have a particle moving like this is moving with some velocity v, I have some magnetic field that goes like this, what's the direction of the force? Right? So this was just applying the right-hand rule. So we said fingers in the direction of v, curl into b, thumb points in the direction of the magnetic field. Now, another way that we could write the Lorentz Force Law for currents is to say that dF is equal to I dl cross b. And what this allowed us to do was to say if I have some magnetic field, let's say a magnetic field everywhere like this, and I have some length of wire, we could say that this is some length of L, and some current that goes this way, we can find what the total force is acting on this length of wire. Okay, and again, we would just be applying the right-hand rule, so we would say that dl points in the same direction as I. Then we would apply the right-hand rule here, and so fingers in the direction of dl, curl into b. That says that the force for this particular example points to the right. And then to find the total force, what we would do is say F is equal to I integral, after I evaluated this cross product, this is dl times b times the unit normal vector. In this case, this points to the right. So this is n hat in general. But then this would be, well, really there should be a sine of the angle here. So this is sine of phi n hat. In this particular case, sine of phi is 1, and then n hat points to the right. B here, for this example, I could say that it's just a constant that comes outside the integral. And so what this says is in the special case where you have a constant magnetic field such that it doesn't vary with the same variables as dl does, then this is just F vector is equal to I times B times L times n hat. Okay. In some other textbooks, you might actually see this written as like a boxed equation, and this is something that you're meant to memorize, but we can see where it comes from if we think about this more in terms of the infinitesimal, and show that this is actually more general than this, because this allows us to do calculations if the magnetic field varies over the same variables as dl. Okay, yeah.
So what do we always define dl as? Like in this case, is dl y hat dy?
Yeah, in this case it would be. But if it was in the x direction, it's x hat dx. If it's the arc of a circle, then dl is equal to r d theta theta hat. But those are really the only three cases that we consider. It's either in the x direction, y direction, or a theta direction for a circle. Yeah. Other questions about this one? Okay. The last equation that we had was Faraday's law. So Faraday's law says, this is number 4, and this is what we've been working on the last 2 weeks here. Faraday's law says the integral of E dot dl is equal to the negative partial derivative with respect to time of the integral of B dot dA. Okay. Now, in order to use Faraday's law, we need to recognize the connection between dA and dl. And so if I had some circle like this, and I say that dA is going to point in this direction, so if I chose dA to point this way, then dl is going to go around the circle like this because it's connected via the right-hand rule. So thumb in the direction of dA, curl in the direction of dl. I also tend to say that the current is the same direction as dl, so when I do the loop is really parameterized by the direction of dl. But when I go around the loop, if this had some resistance of r, then the left-hand side of Faraday's law says that this is I times r with a positive sign. Okay. Now, the right-hand side is where we get a lot of the interesting physics from, because what the right-hand says what the right right-hand side says is that this is the negative time derivative of the magnetic flux. And so what we saw was that there were really 3 different ways that we could get a time-dependent magnetic flux. So the first way was if B was a function of time. Okay? The second way was if A was a function of time. The third way is if the dot product changes with respect to time. Okay. And we've gone through quite a few examples of these. Now, the other thing that I'll say is that so far when we've been doing these dot products, we've been doing them in such a way that we say that B dot dA is equal to the magnitude of B times the magnitude of A times cosine of theta, the angle between them. But this isn't the only way that you can define a dot product. So another equivalent way that you can define the dot product is if I have some vector A dotted with some vector B, where A vector can be written in components AX, X hat plus AY, Y hat, and B can be written in components, these are actually not really related to this B and DA. I just made a choice here to call it an A, some arbitrary A vector, some arbitrary B vector. So if this B vector was written in components BX, X hat plus BY, Y hat, we can take this dot product by just plugging in A here and plugging in B here. And so this is AX, X hat plus AY, Y hat dot BX, X hat plus BY, Y hat. And ultimately, what you have to do is you have to FOIL this. So this is this term times this term plus this term times this term times, or plus this term times this term plus this term times this term. And when I do that, what this ends up saying, because X hat dot X hat is equal to 1, Y hat dot Y hat is equal to 1, X hat dot Y hat is equal to 0, this is going to end up being AX BX plus AY BY, okay? And we've seen this before. We actually used this a lot more when we were doing the flux calculations for the electric flux out of a cube, right? Remember those calculations? I would make sure that you understand how you can do the dot product in this way as well, okay? Any other questions pertaining to Faraday's law? Yeah.
Do you think offhand of a test question that we could go to like do a problem like this?
Sure. Say I give you a magnetic field in components. So I say, rather than saying there is some magnetic field that points in this direction, I give it more generally, and I say that I have some magnetic field. B is a function of T is equal to Bx, X hat plus By, Y hat plus Bz, Z hat. And then I orient my dA in a particular way. So I say that dA, just as an example, dA is equal to X hat dy dz. What's the dot product between these two? This just picks off the x component, right? Because when I take this dot product, x hat dot x hat is 1, x hat dot y hat is 0, x hat dot z hat is 0. So this is ultimately when I do b vector as a function of time dot dA, this is just going to be equal to bx dy dz. Okay. Yeah. So that's kind of an example of this. Other questions? Yeah.
What's an example of the dot product changing with time?
That would be like the loop that's spinning. So if I have some magnetic field pointing this way, and I have a loop that has and this magnetic field is constant. So constant magnetic field pointing this way, and a loop with a constant area, right? So the area doesn't change, but I spin the loop. So what that does is it changes this dot product when I do b vector dot a vector is equal to the magnitude of b times the magnitude of dA times the cosine of the angle between them. This angle is a function of time now. And then that's it. Okay. Other questions? Yeah.
Yeah, like, is there a way we can do an example of like the area changing in time or like the dot product change time? Like, if the area is changing in time, is that something we have to come up with ourselves, or is it going to be something like this is what the dA is?
It's something you have to come up with yourself based on the geometry of the problem. I couldn't say in general, because there are problems that I would never say that the area itself explicitly changes like this, right? So I wouldn't say that A of t is equal to A0 t squared divided by tau squared. I wouldn't do that. But what I might do is I say you have a circular loop and the radius changes as a function of time. That's a problem that we've done before. I'm probably not going to ask a question where the dot product changes as a function of time, mostly because there are variations of the same question, but it's really the same question that we've done already. And the only way that I could do something different would be to make it more complicated to the point that it would be too difficult. So I probably won't ask a question like that. I'd still study it. It's possible I might, but if you were going to wager on it, it's a fair wager that I probably won't ask something where the dot product is changing with respect to time, unless if I think of something that is easy enough for you guys to do. Okay. Other questions? Okay. So let's go back to the question about how we're defining theta hat. So there's a question on one of the old exams where we had some wire, and I'll just make one up because I don't remember exactly what it is. We have some wire that has some current that points out here. So this current points out, and we want to find what the magnetic field vector is at a point AB. So what's the magnetic field at this point? Okay. So this is going to be an infinitely long wire going in both directions. So based on that piece of information, what law would we use to find this? Yeah, so we're going to use Amperes Law. So integral B dot dl is equal to mu naught times I in. And so because the current is going this way, and I want to find the magnetic field here, this is going to be what the magnetic field looks like around the wire at the distance A, at the distance, or at the point AB. And so additionally, we know that the magnetic field should point this way. Okay, so let's go ahead and calculate what at least the magnitude of the magnetic field is. So we know from Amperes Law, this left-hand side of the equation is going to be B 2 pi r, which is going to be equal to mu naught times the current that passes through this. This is just I. And so this says that B is going to be equal to mu naught I divided by 2 pi r, okay, just as the magnitude. But what we want here actually is the magnitude and the direction of this. And previously what I had said was the way that you do this is you say this is a vector and this is a theta hat. But this is generally true, right? Because we could say that this theta hat is this direction that goes around like this. But we want to be a little bit more specific so that we can write the magnetic field in x and y components at this point. Okay, so in order to do that, the first thing that we can do is we can find what the distance is from here to here, right? So if this is some length of A, and this is some length of B, then the distance r is just going to be equal to the square root of A squared plus B squared. So far, so good? Okay. So now what we want to do is we want to figure out what this direction actually is. This is what I'm calling theta hat. It goes this way, but we want it in x and y components. So what I can do here, I can extend this line out here and make another triangle like this. And so if this is the angle theta, this is the angle of 90 minus theta. This right here is the same angle that I have here, right? This angle and this angle are the same. This is 90 minus theta. This right here is 90 degrees. And so this angle here is theta. So what that allows me to do then is to say that theta hat is going to be equal to, this has some negative component in x, so this is going to be minus x component. Is this going to be the opposite or the adjacent sides of the angle? Opposite, right? So is this a sine or a cosine? Sine, right? So this is minus sine theta, x hat. And then in the y direction, this is positive in y. Is this adjacent or is it the opposite? It's adjacent, so this makes this a cosine. So this is plus cosine of theta y hat. So now that I have this minus sine of theta and this plus cosine of theta, what I can do is I can figure out what those are in terms of the things that I'm given, right? So this is the same angle theta. The cosine is going to be a over r. The sine is going to be b over r. So what that says in the end, when I want to write this in x and y components, this is going to be mu naught I divided by 2 pi times r, which is the square root of a squared plus b squared, times the negative sine of the angle. The sine is going to be b divided by r, and so this is b divided by square root a squared plus b squared, x hat, plus the cosine, which is going to be a over r, so this is going to be a divided by the square root of a squared plus b squared times y hat. Okay? And then that's it. So this follows in a similar way to when we talked about point charges, right? So if we had point charges and we wanted to find what the force was acting on them from the rest of the system, or we wanted to find the force on one of them due to the rest of them, what we said was, here's our system of charges. And then the force acting on this one, say, if this is 1, this is 2, this is 3, this is 4. So we want to find the total force F3 total. This is equal to the sum of the forces that act on 3. So this is F3I, where I goes from, well, this is weird because this is in the middle, but where this is, I is equal to 1, 2, and 4. Okay. So that's just to add the force that 1 acts on this one, the force that 4 acts on this one, the force that this one acts on this one. But in order to do that, what we needed to do is we needed to break these forces into components. Well, that's really the exact same thing that we're doing here. The only difference really is that the magnetic field doesn't point from the center of the circle out to the edge of the circle. It points tangent to the circle. And so we just then need to say, okay, well, if the vector points tangent to the circle, how do I parameterize that vector in terms of x and y components? And that's what we did here. Yeah?
And why do we know that vector is tangent to the circle?
It's by definition, the magnetic field goes around the circle. Yeah, as opposed to pointing radially away. That's the real kind of difference between the way that the magnetic field and the way that the electric field behaves. So, and really what it comes down to is Gauss's law. Integral E dot ds is equal to Qn divided by epsilon naught. But for magnetic fields, integral of B dot ds is equal to 0. So what this says is that magnetic fields don't spread from a point. They go around currents, ultimately. Okay. Yeah?
If B was pointing into the page, would theta hat be like the opposite?
If B was pointing into the page, if B was pointing into the page, this would be strange. So if B was pointing into the page, it wouldn't be into the page everywhere. So what I would have to do is, so if I was pointing into the page, then this would go the other way.
So beta, how would be negative? Would be sine the x?
Yeah. Other questions? Okay. You look perplexed.
I'm just thinking if I have any questions.
Okay. Well, we have more time, and I'll stay until you guys don't have questions anymore. I don't have anything else to do today. So.
Like, how long will you be here?
I mean, how long do you guys plan on being here? I'm not going to be here for like 4 hours, but maybe like an hour or two. Oh, you want to like come back afterwards? If there's a gap where nobody's here, then I'll probably be in my office. Okay, so that's it. Yeah.